Thank you very much. So, first time here at this very interesting event. So we have learned a lot of cute things going on. So I think it was really a cute move for me to come to this very cute location, showing some cute stuff also looking cute. So what I'm talking about should be a kind of inspiration, at least I hope that, an idea sharing on how we can do an optimized hardware-software co-design approach. So I'm a hardware guy, so I'm the complement of most of you then, but the challenges we have in the industry are interdisciplinary. So I would like to share with you some explorative ideas we have and hope to get some interesting feedback today. So you see also some nice pictures of the dark side and the good side, whatever, how you call it. So whether software is a bad guy or hardware, I think that's up to you to figure it out. Potentially no side, but what is clear, both need to work together in order to fulfill our customers' dreams. So the outline of the talk is I would like to talk a little bit about digital twins. You may assume digital twins have a certain meaning. You will figure out that the definition is very much dependent on, as Obi-Wan Kenobi said, a point of view. So I will talk about our simulation architecture approach that we are exploring at the moment, model-based system engineering-based hardware tuning that we apply, how we bring enhanced user experience, and how we bring everything together in a multi-simulator aggregation environment. And finally, I will conclude. So this is a picture showing in principle everything what comes next. So digital twins can enable really virtual reality experience at any project stage. What I mean with project stage is development of hardware and software, development of electronics infrastructures, including architectures for vehicles, whether autonomous vehicles or vehicles that bring mobility and transport as a service to the vehicle. Every stage should be reflected via this tool chain and these processes, enabling feedback loops, as we have heard today a lot, also in the CI/CD pipelines, the mismatch or the issues we have in the timeline between hardware and software development, and we will figure out that hardware development is actually also supported by software development, and that hardware itself first is software before it is actually coming into a silicon stage. So we're looking at a logical model approach. So looking at the architecture, on the left side you see a representation of a zonal architecture at this stage, a zone towards the central compute, a physical model, a simulation behind it on the one side. So that's the explorative path that is based on attributes, assuming certain behavior from hardware and software. The next stage is the application software related part, that is the modeling of the customer function. That is also then integrated and used within a virtual simulation environment, in this case Scala or LG-based simulation environment, whatever you use. And then you have the high-fidelity digital twin, meaning that you bring everything of the before mentioned into an environment where you can really experience the car, experience the customer function, while you execute real code that is part of your software, while at the same time, and this is shown below, you have a kind of electrocardiogram to the hardware. So meaning, when your code is executed, what's going on in the hardware? So can you check with that whether your code has a problem or the hardware has a problem? For both sides, we have now a feedback loop that we are exploring, and we talk about now how we do that. So first approach, DEFCON, don't get irritated. We are approaching a missile to the Mars later, that's right. But so we start with the car simulator, with AutoWare and ROS2. So meaning we are trying to build an environment where usually in simulations we simulate the ideal behavior of the functions we intend, also certain mission profiles on the road, accidents, whatsoever. That's a typical situation. Why we use that, the simulator is the virtual environment, the outerwear creates the virtual driver, the sensors, the actuators, the digital representation to that, and the robot operating system is the interconnect environment for that. So it is based on a messaging, a public so a subscriber-based approach, and we have from the simulator some sensor inputs that are given to outerwear, are processed, fed back into the simulation, and then we have, of course, a nice simulation on the screen. So this is a starting point. The next thing what we do, of course, is both have different approaches, the customer functions, whereas the user experience. And in the next step, we extend this. So we add the model-based system engineering tool in order to apply the model to the ideal behavior and try to tune it. Why we do it, the same is we get the input from the simulator towards outerwear, but the key aspect is now that we receive simulation data to the MBSE tool, we do some magic stuff, and then we influence actually with an attributive way the behavior of those sensors and the actuators in the outerwear environment, with the consequence that we have a deviation from the ideal hardware behavior. So this is in principle first a trial approach to see, okay, how can we influence and which parameters I need to adjust which lead to a certain consequence. So here an example. The consequence of what we do was the car parks erratically, which was intended. We modified the parameters. In the other situation, the car parks correct. So what did we actually do? You see this zonal architecture. You see some red dotted lines, very hard to see in the middle, which simply indicate that the bandwidth is beyond the capability of the hardware. So we have LiDAR, camera, potentially radar data that are coming from the zone towards an Ethernet switch, towards the central compute being processed, towards object detection, and then we shift the functions towards the zone, shift the situation formally from a software perspective where calculation happens, and what you see barely is with the blue dotted lines towards the Ethernet switch that we resolved the issue of the bandwidth simply by reallocating functions. So this should give you an idea of you can do this with one function. Can you control it with many functions and interaction of functions with a given hardware infrastructure? So, not enough. We go even beyond and say, okay, we now can tune hardware behavior, but how can we make sure that this tuned behavior is realistic? So the next thing what we do and introduce is, I'm a hardware guy. First, we even extend the experience with an Unreal user environment, as pointed out, for looking inside the car, so from the driver perspective. So what we actually do is we combine simulation and EDA tool chains for chip development and taking those simulators and putting them together in this infrastructure. With the outcome that we now can, in a controlled manner, in a realistic manner, tune those parameters to get a realistic outcome of the modification what we do. Using the simulators, we can do fault injection, we can create hardware glitches, whatever, and see the outcome in the real behavior in an application environment with a given hardware setup. So this gives you, of course, very, very important information regarding architecture decisions, whether you implement better this processor or the other processor, looking at the algorithm, is it more suitable for a different environment, do you hardware acceleration or do it better with software? Now you have that feedback loop. So, and to show you here the enhanced user experience, you see on the right side the Qt environment, so real software. And instead of a camera system collecting data from the road, we used a driving simulator, so the data collected are just analog to being on the road. But you see also you have a cockpit system and an infotainment cluster on the left side, on the right side. And now you see it on the left side. We just streamed those information into the Audi in this case, irrespective that I'm from commercial vehicles. So we will do another model, certainly. But so that means you can experience this real behavior that was programmed by Qt now in an environment, and you don't have the car yet. You don't have integrated that. So you can make you can see how it would look like. So the next step in terms of hybrid modeling and hybrid execution, you see that I took out, say, window opener motor. So that means we also connected real hardware, real drivers to the infrastructure with an Ethernet infrastructure. And now we do some simulation, while in the reality also the execution on the real hardware is performed. So in this case, we have a real software cockpit and infotainment cluster. We have a real Windows system, and now we do the execution within this environment. And first, to understand what we would like to go in the future, of course, for harsh environmental testing, we will go up to the mass. So just as you see, where we will start then the stress testing scenario and the analyst scenario. So this is the environment around the car we are intending to go for. And you can, of course, create whatever environment you would like to use. And then we are now going into the car. You see now that there is a driving simulator running, so that's the driver's view. And then we perform the actual window opening function virtually, and you see on the left side, and also in the middle, barely recognizable how the window is moving. So while this is done, we have the hardware being monitored at that time. So we can really compare whether we have an AUTOSAR stack, an optimized software stack, or a problem, so we can measure what's going in the hardware. So meaning that the call out goes down, that the energy consumption is different depending on the actual software code. So a direct feedback loop between hardware and software. And you can imagine you have a given hardware and you try for this hardware to optimize the software, or you have a software algorithm, especially for autonomous driving, and you try to find the optimized hardware solution for that. This infrastructure could be a solution. A concrete representation of what you have seen is here. So you have a multi-simulator aggregation platform. You have the Kala and the AutoWare environment. You have some hardware processing, of course, that does this stuff, and you have this real hardware hybrid from the cockpit, from the real displays that we have seen, and you have, of course, the environment for Unreal and the environment for the window, which is, of course, real hardware. So DEFCON 1, so that means we're really now ready to launch the rocket. Just to explain to you what we believe is possible, and now we explore it further, is really that for the chips, for the hardware, we have the real representation model available that is also used by the semiconductor vendor before he even gives the model into the manufacturing process. This is done via very complex configuration in the market, which is protecting the IP of the vendor, but it allows us to execute this hardware in a software environment, and it gives a very, very realistic behavior up to 1% to 2% when we do correlation to the real hardware on the table. And this is very interesting because you can then, as you see in this multi-sim aggregation platform, you insert the data, either collected data from the field, from the various camera systems or whatever, and you directly analyze, in this example, based on ARM IP-based architecture environments. So that means for every node in this chip, you get a signature, what's going on in terms of power consumption, in terms of heat generation, and so forth. So you can even extend this. Now, this is another representation how it is done, so I can skip that. But we even can go beyond that. So we have a lot of studies done, for instance, that were assumed to be software bugs, but actually had their reason in a nano crack of a ball from a ball grid array configuration, which of course, depending on temperature and vibration, has changed capacitance behavior, changing the timing behavior of chips, and the outcome is that there's erratic behavior. Very often assumed, oh, we have a software bug. Now, we have the opportunity to simulate with this knowledge. There's a lot of science behind it. We can combine it, and here you see vibrations, shocks, heat generation from the chips, all can be considered, aggregated together, and then in terms of simulation, very realistically correlated to what would happen. So and this extends, of course, the scenario in terms of what could happen. Is your software and your hardware robust? And you can check which improvement opportunities you have. So finally, as a summary, the Sigma P framework, so the sum of all efforts is the product. At the end, we have, of course, as in every development, we have requirements, functional, commercial, technical. We have a development framework, an architecture development framework, which is composed of combining various simulation environments in a smart manner. We simulate, we validate, we do verification optimization, and we use this to optimize the hardware-software platform and have at the same time vehicle mock-ups or the functions we were most interested in available and have this feedback. So, finally, this should give us the opportunity to not only outside manufacture good-looking products, but also in the future have inside an environment that is much more innovative and user configurable, which we are looking for to go in a transformation phase with the Volkswagen Group and commercial vehicles. Thank you very much for your attention.